Okay, so let's work through these problems. All right, so the first one, are we going to get that? Looks like the logical answer. But no, so what's wrong with that answer? Yes. Right. So there's going to be a carbocation rearrangement here. And so the carbocation that's going to get formed initially is this. And we've got a hydrogen there that can do a rearrangement. Yeah.
People are so loud.
Okay, and then we can do the sort of normal addition and elimination thing. But let's see. There we go. For this one, we don't have to worry about a carbocation rearrangement. And so we're just going to get the cyclohexyl group substituted onto the benzene ring. And then, so we just started talking about the Friedel-Crafts acylation last time. And so the intermediate here is this, the acylium ion. And the nice thing about this is that it doesn't rearrange. And so in this case, we can just sort of plug and play. And we don't have to worry about doing rearrangement. Okay, so and this product up here, yes?
You might be going into it. I was just going to ask, I'm just a little confused on like with the rearrangement of the first one compared to the like not having rearrangement. I'm confused on just like how you get like the rearrangement of the first one.
Okay, let's draw out the whole rearrangement mechanism for that first one. I think that will make more sense. Okay, so we're going to start with the first step is going to involve just the alkyl halide and the aluminum catalyst. So it's going to coordinate to the metal like this. And then we're going to break this carbon-chlorine bond. And so the initial carbocation that we generate is that. So this is primary, which is not happy. And it would like to rearrange if possible. So if we look at sort of the other places where we could put this positive charge, we could have it go here. That would be a secondary, and that's certainly better than primary. Or we could put it here, and that would give us a tertiary carbocation, which is the most stable. And that would be the ideal case. So let's see if we can actually do that. And to do that, we'll need to draw out the hydrogens, if any, on that carbon, the most substituted carbon in the molecule. And now in order to get the positive charge over there, well, we're not moving the positive charge, we're moving electrons in the opposite direction. And that causes the positive charge to move. And so we're going to break this bond. And instead, we're just basically we're just shifting the hydrogen over to a different carbon. And so now we've made a CH bond there. And so this carbon is happy, it's got an octet, but then this carbon has had something removed from it, and so now it's got a positive charge. So this is tertiary, which is good. And now we take our benzene, and it's going to attack this electrophile. Two methyl groups, and then like that. And now our aluminum catalyst come and take a proton, and then this forms double bond, and so now we get our aromaticity back, and we're all happy. Does that help? Okay, cool. Okay, so this molecule that I proposed as the answer to the first question, based on the Friedel-Crafts alkylation, we can't make that, because if we try to use this alkyl chloride, it'll just rearrange and we're going to get the wrong product. But it turns out we can make that molecule, and we just have to use the Friedel-Crafts acylation to get that carbon fragment on there, and then we can remove the ketone. So let's do that. Okay, so actually we want that, okay. So we're going to have an acid chloride of some kind, and the carbons that we attach have to be basically the same. So that's what we want to attach, this group here. And so essentially we're just going to use this same molecule but with a carbonyl right there. So that's going to be that molecule. And so because we're doing an acylation, we don't have to worry about carbocation rearrangement. So we get that. Now, of course, the main problem is that we've got this carbonyl and we want to get rid of the carbonyl. So we're going to do a reaction called the Clemenson reduction. And this is going to involve, I'll put it down here. Zinc amalgam, so zinc and mercury alloy, hydrochloric acid, and some heat. And that just replaces the C double bond O with two CHs. And so, in effect, it just kind of wipes the carbonyl off the face of the earth. And so now we've got this alkyl group that doesn't have the most substituted carbon attached to the benzene ring. So if we do the Friedel-Crafts alkylation, we get this. But if we do an acylation with essentially the same carbon-containing starting material, this versus this, then we can get that molecule that maybe we wanted. Something like that. So that's going to be a strategy that you'll need to look for when we start doing synthesis, is if you see an alkyl group that under normal conditions it would rearrange, then you're going to have to think about maybe doing an acylation and then reducing the ketone. Questions on that? Okay, so we have talked about doing reactions on just benzene, right? Just straight up benzene. And we haven't had to worry about where we're going to put the alkyl group or the nitro group or whatever, because it always just goes somewhere on the benzene ring and it doesn't matter where it goes. Sadly, that ends today because we're going to start doing reactions with substituted benzene derivatives. So, as an example, let's take toluene and try and do a nitration. So now, instead of just sticking a nitro group on wherever we please, there's 3 different positions that we can possibly put it on. What are those called? Orthometapara. Yep. So we have 3 options here. There's the ortho, meta, and para isomers. Any guesses for which one is going to be formed the most?
Maybe meta.
Turns out it is not quite as logical, or, you know, I don't know. This is not a guessable thing in my personal opinion, so I kind of tricked you there. But ortho is formed in 63%. Meta in just 3% yield here, and para 34%. So what you'll notice about that, obviously meta, we have essentially no formation of the meta product. And then as far as ortho goes, it's roughly twice what you get for para, and there's just 1 para position at the bottom, but there's 2 ortho positions, these 2 at the top. So what that's kind of implying is that the methyl group is sending the nitro group to either the ortho or para position. And that is the case. So if you were to draw out resonance structures for the intermediate, you'd find that the ortho and para-arenium ions, the one where you've got a positive charge on the ring, one of those resonance structures is particularly stabilized because you end up with a positive charge on the carbon at the top here where the methyl group is attached. And because the methyl group is an electron donating group, that increases the stability of that resonance structure, and so those resonance structures are more likely to react. So these are called activating groups. Essentially, that's the same as an electron donating group. It's called activating because it makes the benzene ring more reactive, at least slightly. And we'll talk about specifically which ones are which. But because of that resonance structure, activating groups are ortho-para directors. So that means that if we take toluene, or if we have sort of any other electron donating group already on the benzene ring, and we do any EAS reaction, any electrophilic aromatic substitution, whether it be nitration like this, or Friedel-Crafts alkylation, acylation, sulfonation, you name it, you're going to get a mix of ortho and para products, but very little to none of the meta product. And so that's good because we can use various groups on the benzene ring to control where other groups end up going. And so that's going to be another synthesis strategy that we'll see. So, what if we want to do meta? In order to get meta substitution, we need a deactivating group. And in the same way that activating groups are electron donating groups, deactivating groups are generally electron withdrawing groups. So, an example of one of those is CN, nitrile. So if we do this nitration, we get 6% ortho, 1% para, and 93% meta. So the identity and electronic properties of the substituents have a huge effect. 93% versus 3% on where other groups get put. Okay, so activating groups are ortho-para-directors, so deactivating groups are meta-directors. Yes?
Do we know like a good, is there a reported set of known deactivating groups in the nice.
Yes. Okay. As with all rules in chemistry, there's an exception. But I think it's a pretty easy one to remember. I think. That didn't mean anything, really. And it's halogens. Halogens are deactivating electron withdrawing mainly because of induction, but whatever. So they're deactivating groups, but they're actually ortho-para directors. Okay, so Maddie had a good question. How do we know what's activating and deactivating? Well, there is this handy dandy chart. Oh, and it's plastic. It's too big to fit in. So there's a copy of this on Blackboard, and some of this I think will kind of make sense just based on the structure of these groups. Some of them may make a little bit less sense. Okay, so as a baseline, we've got a hydrogen, which doesn't do anything. That's just, the absence of a functional group. And so as we go up, we have groups that are more strongly activating, more strongly electron donating. And those are ortho-paradirectors, of course, the halogens being the exception. But everything up here is an ortho-paradirector. And in addition to these being more strongly activating, they're also more strongly ortho-para-directing as you go up. So having an R group, like a methyl group or something like that, is a moderately strong, or really we'd call it a weak activating group, and is also a weak ortho-para-director. So it has somewhat of a smaller effect, but it will still provide ortho and para as the dominant products. And then the opposite is true for deactivating groups down at the bottom. These are meta-directors, of course, with the exception of halogens. You'll notice that a significant number of these have a carbonyl group directly attached to the benzene ring. And in that case, there's no exceptions really to that rule. If you have a carbonyl directly adjacent to the benzene ring, that's going to be a deactivating group and a meta-director. Now, one thing I'll point out is esters and amides. So if the heteroatom, the nitrogen or oxygen of the ester or amide, is attached to the benzene ring, then that's an activating group, and it's an ortho-para-director. So something like that. On the other hand, if the carbonyl carbon is what's directly attached to the benzene ring, like that, then that's a deactivating group and it's a meta-director. Okay, so you're going to want to have this chart handy when you're doing homework and stuff, because that's going to help you get it in your brain as quickly as possible. Okay. Do I have a room here? Not really. Okay, so the situation gets slightly more complicated when we have multiple substituents, but I'll show you a simple example first. Okay. So let's say that our starting molecule is this, and the reaction we want to do is a bromination. Okay, so the best way to analyze this is to look at each of the substituents on the starting material individually and see what they're going to do, and then combine all that information to make a decision on the final product. Okay, so let's look at the methyl group first. If we look on our chart, R is just an alkyl group really of any kind, so that's an activating group and an orthopara director. So OP meaning orthopara. So all right, so it's going to want to direct toward the ortho position. There's two ortho positions. What about the para position? It's blocked. So in this case, right, we're not going to substitute the nitro group for something else. That is not a reaction that happens in this case. So the para position is blocked by the nitro group. Okay, so the methyl group is going to direct toward those two positions. Okay, the nitro group is the king of deactivating groups. It's the most strongly deactivating group that you can have. So it is also a meta director. All right, so the meta positions from the nitro group are where? Yeah, so the meta groups are there. And they're not blocked by anything, so that's good. Okay, so in this case, both of the directing groups are going to direct our new group that we're introducing to the same place. So for us, that's good. Both groups direct into the same place. And that means that is going to be our product. You can put it on the other side if you want, but it's also the same position, so it doesn't really matter. Okay, how do we like that? Is this okay? All right, so that's a good situation where we've got multiple things all pushing the bromine to the same spot. Yeah.
You just draw out what the final product is.
Yeah.
Okay. So it wouldn't sub to both.
They're identical.
No, I'm saying that you wouldn't, since you have the NPR2, like, have like coming off. So not space, right?
Correct. This is assuming you're just doing one equivalent. And so, yeah, if you were to do another equivalent, well, now you've got to take into effect the bromine, and that's a halogen, and it's a deactivating group, but it's an orthopara director. So then you're going to have some competition going on.
I see.
But yeah, good point. We'll just add one group at a time, and maybe in multiple steps, but okay. Okay, so what happens when the two groups are pointing toward different places? All right, so this one is a nitration reaction, but the type of the reaction doesn't really matter because we're focusing on the effects of the directing groups rather than the reagent that we're using. Okay, so we'll start with the OH. So the hydroxyl group is, there we go, it's an activating group. And I'm going to go ahead and compare it to the methyl group because, as it turns out, the methyl group is also an activating group, but it's a little lower down, a lot lower down. So the OH is a pretty strong activating group, and the methyl group is a weak activating group. So strong activator, strong orthopara director. So the ortho positions to the OH are there and there, and the para position is here at the bottom, but it's occupied by the methyl group. The methyl group, we said, was a weak activating group, or at least weaker than the OH. Going to be a weak orthopara director. Up here we can also denote that those positions are being strongly favored by just putting an S next to them because the OH is pointing toward those groups and it's a strong activator, so, you know, help us keep track of everything. Okay, so the methyl group is also an orthopara director. The para position is taken by the OH, and the ortho groups, or the ortho positions, are right there. And the methyl group is a weak directing group. So those positions are being weakly favored. All right, so now all we have to do is kind of put this together. So the OH group is a stronger director. So its effect is going to dominate. And so where are we going to put the nitro group?
The one's closest to the hydroxyl. Like,
Yeah, at the top. All right, so work through that one in the last couple minutes. Make sure you don't necessarily have to, but I would recommend drawing out the little diagram for each of the groups. Okay, where does it go? Northeast, south, or southwest? Southwest. Okay, we're going to do, we'll walk through this at the beginning of next time, but before you go, I want to show you, come on. Come on. I want to show you the homework. So I posted the homework. You don't have to do all of the problems. You just need to do the ones that it tells, well, okay, on the first one you have to do all of them. But all the ones that are bold and starred are the ones that you have to do. So like for the mechanisms, I've only asked you to do 3, and then the rest of them you can, probably should do for practice. But it's a lot, so I didn't want to make you do everything. At this point, you should be able to do the whole thing, with the caveat that we haven't really talked about synthesis yet. But we've talked about all the reactions that you need to do these. So some of these are fun. All right.